All right, good morning. I want to thank the organizers for inviting me. I feel a little awkward in this crowd because I am not an electrochemist at all. But I was asked to talk a little bit about data science and its impact in the optimization of electrocatalytic and battery applications. And so today I'll tell you a little bit about our tools in data science, but I'll also mention some more broad applications of it. Mostly what I will speak about is actually non-continuous variables, so this would be molecular structure. What we just saw in the last talk, beautifully illustrated, is continuous variables and how you can use different types of learning algorithms to optimize for those. I will do then a short case study in electrocatalysis. This is work I did with Shelley Mintier. And then a short discussion on flow battery materials. This is work I did with Shelley as well as Melanie Sanford. And then finally, I'll spend some time on philosophical and thoughts of the future of how we can use data science more appropriately. All right, so I'm going to start off with the workflow that my group uses. This is fairly common in the field of data science and molecular structure. And what we usually think about is taking empirical data that we collect or someone else has collected and thinking about it in one very specific form. This is very unusual for organic chemists, and that is no wasted data. Usually organic chemists ignore zeros. And in data science, you cannot ignore zeros. Zeros and ones have the same very much important statistical implications, and so I'll speak about that a little bit. The other aspect that I think is really interesting here is when you're optimizing a reaction or some sort of material, you want to look at all features. So this could be, in the case of a catalytic process, the substrate and the catalyst. This could be the membrane. This could be the solution that you use, the electrolyte in an electrochemical cell. All of these things have to be somehow featurized. This leads to a great question that was actually brought up in the last talk beautifully, and that is data set size. And so big data, which is something that we do not do actually in most of chemistry, what we saw with taking the gigabytes of information, that is big data. We usually have small data set size, and so that's because we have to either develop a way to make the molecule that we're going to test, so that's a synthetic problem, or we have just very few opportunities to run the reaction. Our assay is very slow, and let's say we can only gather hundreds of data points rather than a million or billions of data points, which would be required for effective use of certain learning algorithms. The other aspect is data set quality, and I won't speak too much about that today. I'll mention a little bit at the end of the philosophical section. This is a real issue if you're going to do data mining. Data mining in our field, especially synthetic chemistry, is bad at best, what's in the literature, because most of these things are done as one-offs. There's a massive error bar associated with it, and also sometimes it's not even reported as a correct reaction, so these are things that we can talk about later. But if you're going to use data science and molecular features, you have to find a way to featureize, and this is what my group has specialized in the last decade or so. Really, what I will just briefly mention, then I'll show you in the illustrative examples, is that the molecular features we use are from physical-organic chemistry. And why we chose these rather than the kind of traditional features that people use in molecular structure, this is topological and other types of features, is that we really want to know why the current fitting leads to the performance. So if you take this data and features that have relevance to their structural capacity, you can then regress and come up with an equation. I'm showing you a linear fit here, but there are all types of machine learning type algorithms one can maybe use. If you have a way to do this, ultimately you fit the data, hopefully it's predictive, and I won't speak about that in too much detail until later. Oh wow, that's a good typo. You can do the idea of what I'm terming here transfer learning. Now, transfer learning and machine learning has a very specific connotation. What I mean by this in chemistry is we can take this equation, which is essentially just a fancy Hammett plot if you're an organic chemist, and can you take the information related in the coefficients and the parameters and turn it into mechanism? And the reason one would want to do this is twofold. One is it gives you much more, I would say, strength of argument to do a predictive extrapolation. But more importantly, let's say your actually high point is 60% yield in something, and you're stuck there with the molecular features that you have put into your starting molecules. What you need to do is transfer that or translate it to a new molecular structure, and the only way one can do that is if you understand what is going on in the reaction, so the mechanism in the end. So I'll show you this workflow in action in 2 very short case studies. But before doing so, I want to show you a little bit about the features we use. And I would say this slide is actually relatively old these days. I didn't want to go through all the features we collect. In some campaigns, we're collecting hundreds, if not more features. But what we usually do is we look at physical features of molecules. So this could be a steric parameter. And for some of you in the audience, you may be familiar with this. We usually use DFT structures. So we compute these structures. These are usually minimized structures. We actually now look at conformational effects in these molecules. We can include that into our analysis. And this is one that we've used a lot. It's called sterimol. It's an old one. Torsion angles, distances, percent vary volume. These are all features by which the molecules are being represented. But more importantly, what we also include are quantum mechanically derived parameters. And these are the ones that really get you to the meat of the operation. This is an MBO charge, point charges in general we look at. But I think the parameters that have been very successful for us are hybrid parameters. So this would be vibrational frequencies. These are all things you can calculate relatively easily. NMR chemical shifts, things of the sort, bond association energies, whatnot. We can include these all in the same spreadsheet that we will then regress against the output of interest. And the algorithms that we've developed that are based on very simple algorithms are stepwise forward fitting functions for linear fitting. We do use machine learning, but I won't speak about that today. That's obviously a consequence, and we already got this discussion last time, of the size of data sets that we can actually get our hands on most of the time. So I will now talk about our first case study, and I want to talk about the backstory here because I am not an electrochemist, and the only reason I can talk at this conference is Shelley Mateer. She forced me to be an electrochemist, or at least my students and postdocs. I think many of you in the audience probably feel the same way. And so the first question she brought to us, and I still love this question, is can we develop a system to take glycerol, the biofuel fuel source that Shelley spoke about in her seminar, and connect it to an enzyme and a small molecule catalyst. And my job was to identify the small molecule catalyst and then ultimately optimize it. And in this idea here is oxalate oxidase takes this set of reagents and does oxidative cleavage to ultimately form CO2 and some energy. And what we needed to do is find a small molecule that would be compatible with with oxidase and do this in an aqueous system and not chew up the enzyme. And ultimately, we did identify tempo. And what was an interesting feature of this is we screened a number of commercially available tempos, and amino tempo was the only one that was satisfactory in this situation. And that can be kind of shown here in a very crude way. Tempo amine has the best catalytic activity under the aqueous conditions by which we were doing these fuel cell studies. And these other ones that are kind of traditional in the field of organic chemistry are structurally really different, at least from the first approximation. But you can see that they're active, but the redox potential is different. So one of the questions that we started coming up with at this point is, how do you know which one of these is going to work and in what context will it work? And that led us to think about the structural features of these types of molecules as a consequence of catalytic activity and redox potential simultaneously. And so if you want to just look at this mechanistically briefly, and I won't spend too much time on this, but nonetheless, this is the electrochemical cycle of an oxymonium and the chemical cycle. So you oxidize it to the oxymonium. This is the active species in solution. This is presumably going through an intermediate like this, which then eliminates to give you the aldehyde, and it gives you this species here, which is a really interesting consequence of this reaction in aqueous conditions. Is if you're under acidic conditions, you protonate it. This takes it out of the cycle. If you are too basic, you get here, and the question is, can this electron transfer occur here, or does it occur there? Nonetheless, we can measure these types of electrochemical processes with CV. So CV is a wonderful tool. I don't think I need to preach to this crowd on this. But as an organic chemist, all we used it for was measure redox potential. But it turns out you can get kinetics and other interesting information. Wow, this was a surprise to me when I first started doing this. And so this was the first scan we did. This was not work done by David Hickey. And in this first scan, you only see really one event here. You see this little hump. And what, again, this is something an organic chemist doesn't think very much about, but you change the scan rate, and all of a sudden it presents the second hump. And this redox event is the EA2. which is this oxidation, and EA1 is this larger event here. And these two, being able to take these two pieces of information from a singular experiment allows us to start thinking about the data science aspects of this. And so my lab, in collaboration with Shelley's lab, but mainly my lab, made all of these molecules. These are all the commercially available or synthetically accessible ones, with a few bonus ones that we made along the ways. And I would say from an organic chemist's point of view, you would look at this and say there's no way you could correlate all these catalysts, right, classically. We would look at this and say these are structurally really different. And in first approximation, absolutely. So the question is, how do you correlate it? And so we did this in a two-step process. The first step was the empirical process, where actually David Hickey showed that if you measure EA1 and EA2 and you take the difference, this is the inverse difference, you get a very nice correlation of catalytic activity of these processes. And I won't dig into the exact features of why this is occurring here, but nonetheless, this is an empirical observation. But what we wanted was a computational observation to allow us to then predict which each catalyst would do, and then ultimately extrapolate if that's what we wanted to do. It turns out we made enough of these derivatives that we didn't need to extrapolate for this particular application, but later on these were very useful in future applications. So we parameterized this, and this turned out to be a very easy parameterization in the end. That's not how they always go. We parameterized the intermediate by taking DFT calculations of the oxymonium species. And essentially what we find is the IR stretching frequency is correlative with EA1. So we can get the EA1 computationally directly just by computing the oxymonium. This is the active catalyst species. And EA2, besides these suckers out here we can talk about later, EA2 is also correlative, but now you get the IR stretching frequency of the radical itself. So now you have a way to anticipate EA1 and EA2 and therefore predict the performance of any nitroxyl radical for these particular oxidations. Very simple, actually, in this particular instance. So what this allows one to do is then to categorize these. And, categorization is nice, I think, and this is a beautiful plot that David had come up with, where you can position what each type of molecule set will be good at. What's funny to me is Temple is essentially the worst at all of them, and that's the one that everyone uses because it's commercial. There are a number of commercial ones on here now that are not as cheap, but Tempo is the worst one. So we can help design such catalysts. So that was the first very basic case study. Let's take it to another, I would say, a little more complex situation, and this is work done by Christo. Christo, you're in the back? Yes, Christo is my collaborator when he was at Melanie Sanford's lab as a postdoc, and now an independent investigator. And this is the area of flow batteries. I think this is an audience I don't have to do a full flow battery introduction. When I talk to organic chemists, they have no idea what these things are. But nonetheless, what we wanted to be able to do is take the same kind of workflow and predict the stability and electrochemical potential of different electrolytes for flow batteries. And here's the interesting rub, and as an organic chemist, this is one of the coolest things we get to think about, is we need a molecule that's stable in charge and discharge form, but we also need one with incredible energy density. And that is a problem, because what we teach organic chemists is high energy density equals unstable. Those are correlative. So how do you get around this? And obviously there's going to be some structural features that one could find in an organic molecule to do this. I should note this is non-aqueous flow battery chemistry, so we're looking for molecules that are only organic in this particular application. All right, and so our study started with working with Melanie's lab, and Christo showcased that these molecules look like really interesting candidates. These are acyl pyridinium salts. Pretty easy to make for the most part, and they have beautiful redox potential. But unfortunately, when you cycle at least the parent molecule, it cycles pretty well for about 3 or 4 cycles, and then it starts getting chewed up, and that's obviously not going to be any use for a flow battery. And so this is where we started thinking about this. And so what Christo did was to make a measure a variety of analogs. And so I'm just going to mention briefly, there was a training set design here. The training set design was extremely simplistic, and that is we are using a Hammett series, but obviously we had to think about functional group tolerance for such scenarios. And then we looked at anything on the N-alkyl portion of this catalyst. And just to kind of showcase this in really simple terms, is if you look at this series here, I've just organized it by KREL, so relative rate of decomposition of these. KREL gets slower to decompose here, but you can see that's correlated with the E1/2. Exactly what we expect. Less stable, more energy dense. All right? And this kind of breaks right here. This is a really cool observation. It breaks right here where you go with ethyl, isopropyl T butyl. You can see you get almost 2 orders of magnitude of stability, but the E1/2 is not affected as you would expect. And what this suggests mechanistically, and this is something that inspired our parameterization, is that the radical dimerization presumably is occurring here that leads to decomposition of these. This is protecting something. That's what we had anticipated. So how do you parameterize these is the next question. And again, we use a variety of different features that we are commonly using, and including electrochemical potential, which we compute, again, fairly easy and straightforward for us to do. But what was exciting, I think, is we had to come up with a designer parameter. And this is where having an organic chemistry iSet is really useful. And the designer parameter is a really simple one in the end, and that is we looked at the height out of plane of this substituent here. Okay, none of the steric parameters that were in the literature actually describe this. That's really interesting, and this is a long and sordid history in organic chemistry of steric parameters. And what you then find is that you can fit the data, which is depicted here, with 2 parameters. Okay, so it's a multivariate linear regression fit. And I love this example, one of my favorite we've ever done, because E1/2 is an electronic parameter, but it's also a measurement of thermodynamics, right? What's also exciting is this HST is a steric parameter, but also it's a measure of kinetics. So we have broken this up into a really simple analysis of what is going on in these molecules. The kinetic consequence of putting something here is slowing down dimerization, and then these are coupled. So the question is, can you decouple them at least modestly? And so the first stages here, we did a very quick interpolation, and this is what we often do in our data science stories. You can note these are very small data sets, and that's because these are not simple measurements, not simple molecules to make. So you're kind of stuck here. All right, and so I like this one particularly because this is a group that you would not necessarily put in a Hammett series because it has ortho substituents and it's rather bulky, and we predict it reasonably well. But then what we did instead of interpolate is we extrapolated. In this, we needed a virtual screen. Okay, so we do a virtual screen. This was all done by hand, and this is almost 4 years ago now. In our more modern instances, we actually can do this in a much more effective way using some data science tools. And the virtual screen led us to these 2 molecules. So this one right here, this is focused on this one, is incredibly stable. You'll note that it's stable on the order of months, half-life, and Crystal was able to crystallize this, which I always find exciting. And more importantly, we're able to improve the stability of this type of molecule 1,000-fold. Okay, that's a massive extrapolation. It's 3 kcals per mole about. Now that said, you probably will guess, if you've been paying some attention here, that this also comes with the caveat. And the caveat is, it turns out this has the worst E1/2 of the whole bunch. So again, redox potential is correlated with half-life, at least modestly. And what we really would like to do is stick a substituent or a compound out here. So this led us back to do another virtual screen. And this virtual screen simply looked at now adding additional substituents to the pyridine core. None of our molecules in our training set had this. And so this was a risky, I would say, extrapolation. Nonetheless, this is the molecule that we chose to look at. And the redox potential now is looking quite excellent. And the stability, as you'll see on the next slide, is still much better than our original set of molecules, but not quite as good as the one I just showed you. And ultimately, it predicts nearly perfectly. So from a data science point of view, this is an exciting result. It also is an exciting result as it is now has minus 1.21 volts as a reduction potential. What I really want to point out here, just briefly to finish this section, is this is my favorite part. I teach sophomore organic chemistry. And I always tell them to ignore ethyls and methyls because I don't want them to get stuck in the weeds, right? So this is interesting in that if you go from ethyl to methyl, you lose almost 2 orders of magnitudes of stability. And this, our model predicts nearly perfectly. And the reason for that is the methyl group cannot be out of plane. So the ethyl group is now out of plane. And this very basic feature of it is what makes it a good electrolyte. okay, a stable one. People have asked me about the isopropyl group, and Crystal will tell you putting an isopropyl group is not simple. But nonetheless, our calculations don't tell us we're going to get a whole lot more out of it, so there's no real reason to make it. Another reason to use data science, so you don't have to make something that's going to be a pain to make. All right, so I will finish now with a few slides on what has been happening recently, and then a lot of thoughts on data science and chemistry, especially molecular chemistry. So I unfortunately won't have time to go through all the details here, but my postdoc, Chris Sanford, and Shelley's team, and I just really want to give a call out to Lydia and Tyler. One was a freshman, one was a sophomore, and they did all the physical measurements of the rates that were required to do this chemistry. But nonetheless, what we were looking at is the ability to do a reduction of cobalt-2 to cobalt-1, and then the chemistry of cobalt-1 that's ligated in a bidentate manner to a ligand class that my lab likes to think about. And what we want to be able to do is use this in cross-coupling reactions, but we were finding in our empirical screening nothing was occurring. So we went and did a deep dive, and we found that disproportionation was a problem, and we figured out what ligand classes would perturb that in our favor. These are chiral ligands, so I should note that. Also, what we've most recently done is looked at the mechanism by which oxidative addition occurs, a fundamental organometallic step. And just to kind of briefly, and Shelley can answer these questions if you have them, because she's the one that helped Chris do this. But briefly, what we were able to do is measure CVs of these processes, and we can simulate them and see if the mechanisms we propose fit with the CVs that we are observing. And I think this is really quite exciting because it's not, again, a tool that an organic chemist normally would use to probe mechanism. You have to have some data, obviously, in the front end, rates and such like that, to put into these simulators. But nonetheless, this is a very powerful tool. From the point of view of my group, what we're also able to do is simultaneously change the catalyst and the substrate, and we can build correlations. I won't do a deep dive here, but we were able to explain what all of this means in the manuscript that just got accepted. What I really want to point out here is we start with aryl bromides as the training set, but we were able to extrapolate to aryl chlorides and really unusual substituted aryl bromides, so we can get the rates and predict them based on the parameters of both the catalyst and the substrate themselves. Again, this leads us to hopefully solving the catalytic problem that we're interested in solving. All right, so I have one last slide, and I have lots of thoughts, and we're probably over time, and it's coffee break time almost too. We don't want to screw that up, but lots of thoughts on this. So applications of data science and chemistry, and again, this is more from the molecular side, but you can also imagine the type of optimizations we saw in the last talk, design of experiments on crack is like what I like to call it. So structure-function relationships. I showed you two structure-function relationships today. We use this all the time, but the applications of structure-function relationships are pretty much all of organic molecular chemistry, okay? There's a lot of push in the field for synthetic route planning, so how do you actually make the molecules that will end up in your structure-function relationships? That's a massive field. Obviously, optimization of particular reactions. There's a work that my group is working on with a couple companies, autonomous reaction optimization. Novel reaction prediction is something that we would all love to be able to push. And then feature predictions. These are something that the people more on the computer science side are really excited about, including my group. But the issues are broad, okay? The issues are broad in our field. Data quality and quantity, okay? So if you're going to use a sophisticated learning algorithm, you need data, lots of data, because most of these require, a neural net requires information that can be correlated. And if it's a nonlinear fit, you don't know what that means at the end. And so this is a massive ordeal in the field. We have also this problem, and this is probably the most important problem to point out to this audience, is data bias. So in the molecular sciences, we report, because this is how we get our grants funded, we report what works. And I do, because that's how I get my grants funded. We do report, I do report, and we are more aggressive about this, ones that don't work. Phil does. He reports. He has tables and tables of stuff that doesn't work in his SI. These shouldn't actually be relegated to an SI. This should be relegated to some place that people can data mine much more effectively. And that's something I hope that the community is going to work on. I know Google's very interested in this, actually, so hopefully that will solve all of our problems. How do you select features? I just showed you today the way we are selecting features seems to work. Obviously, there are examples where it doesn't, but feature selection is incredibly important, and that would allow you to use more sophisticated learning algorithms if you select this correct feature. This is something I get all kinds of interesting questions on. I'm not a data scientist. I'm not an electrochemist. I'm not a computational chemist. I'm a chemist. And I really think that people who don't think we can do this are silly. Data science is math. Right? And yes, you should know what you're using, and it shouldn't be completely black box to you, but most of our students took math much more recently than we did. All right. This is the other part that I love talking about, and I won't spend too much time today. AI versus ML versus data science. You note that I try to use the term data science because I'm using the all-encompassing term. A lot of people misuse some of these other terminologies. It's not my place to fix that. But that leads to this problem, is don't believe everything you read. It's pretty frightening what people write. All right. So I just want to point out the two things that I think are really important. We are data starved. Okay, there are so many people that want to try their new system, and we are so data starved. And electroanalytical tools are actually one of my favorite ones now to try to use because they give you more than one output. Right? It's not just a rate. They can give you thermodynamics at the same time and a number of other variables that you can adjust for and have an output. So it's data rich. This is really nice. And a lot of the tools are fast. Okay, the faster the tool and more accurate the tool, the better off you're going to have for data science. So that's one point I want to make. And this is another one that my group is really hammering on these days, is how do you design the data sets before you even start the project? We don't care if it works or doesn't, it turns out. We just need to design it in a way that you're getting data that's statistically relevant. And the way we're doing that is we featureize the molecules and the processes first. That will help us design what the data set should look like so you can do a minimal number of experiments, a lot like design of experiments, to help you get to the data science goal. That is the idea that we are pushing forward, at least in our research. And again, features are really an important part of this. If you know how to featureize the molecules and or the conditions, you have a way to do a much better design in the future. And again, engineers in this room get this. Chemists don't. So I will finish there and thank this wonderful, amazing group of people who are a mixture of mostly organic chemists trying to learn data science. I need to thank, I have a really incredible laundry list of collaborators. I point out Shelley and Melanie. I didn't talk about Dean today, but Dean was involved in a little of the battery stuff a little later. I want to thank the NSF in particular because NSF, this grant right here, which isn't part of this study so much, but this grant right here was my one person in the back of the lab who started a data science project about a decade ago, and it's been awesome. That's led to all these other opportunities, including the work that I talked about with the DOE and ARO today. And I would be happy to take questions or just run out here and get a coffee. I thought we were going to do a little dance.
That was a great talk. Very little room for questions, but there are some.
Hold off on the coffee, Matt. Molecules are so much more defined than a nano thing or an actually high-performance electrocatalyst or battery material. So what advice would you give for us to move away from the well-defined world?
Yeah, so what we're starting to do is use molecular dynamics as at least a starting point to parameterize. The question there is I am not in that field either. I have a student who's looking into how we do this, and we're working with one of my colleagues at the University of Utah who is an expert in MD. This is a much tougher problem. I mean, we're using this for interfaces. That's where it's the same problem, right? Interfaces. And if you know some of the molecular structure, can you use the force fields and the features by which you can gather from that to give you the right parameters? The answer to that question is I have no earthly idea yet, but my sense is, I mean, this is why we're trying it. So I think my sense is that's the way to go, but I don't know the answer. Tough problem, but not impossible.
Molecules easy.
I would disagree with that, actually. Molecules are not easy. Sure. My disagreement would be if you take all the molecules involved in the catalytic process and you don't know what the mechanism is, it's a lot less easy. But it's the same problem. The scale is the problem. It's a scale up. Molecules have not been easy for us.
Other questions?
Wow, I silenced the cloud. That's good.
Actually, I have one question. So you mentioned all the
Yeah.
all right.
You're being recorded.
So you mentioned the issues with data that you see that are going to be a problem, and certainly those issues are very general in all the science that I've seen so far. Now, one thing that you didn't mention was data integration, when actually you have gather data from different instruments and things like that. Can you comment a little bit about that?
Yeah, I certainly can. This is a question I get all the time, and I should put that on my slide. Yeah, this is a massive problem as well. There are, again, teams like Apple and Google and a lot of the big pharma companies, at least the ones I interact with, are extremely interested in how we're going to deal with data integration. I am not touching this one, so because then you have to deal with the companies who make the instruments and the proprietary aspects of that. But in the end, you want every piece of data you can get out of anything, because that's how data science is going to be effective here. Oh, there's one more.
There's one more.
Yeah, there are a couple of trends that you didn't touch on, but maybe you have some interest in. And one is using the data science to highlight the features for you. You talked about the great cases where you could develop features in advance, but there are automated featurization schemes. I wonder if you could talk about that. And the other thing is active learning, where the data science tells you which data to go and get next.
Yep.
You know, how much of that do you feel that's relevant to chemistry as well? So
active learning first, absolutely we're doing this, yes. So we're building active learning processes right now. So the problem is there's a lot of people in the field now too as well. So my group is mostly focused on featurization, but we are working with other teams who do active learning. The first question is yeah, absolutely. Feature collection as a data science tool is exactly what we're doing as well. So I have one program where we have computed DFT properties for a wide range of important molecules, and then can you fit that somehow and then extrapolate? Very classic machine learning problem. Those are the kind of problems that machine learning is really good at. It's a little less good at some of the things I showed today. Again, because of the data set size. But if you can get computations as your kind of data set, then you have this much more effective data science goal. Yep.
Okay, with that, let's thank Matt again.
Right.